Good morning, dear student, and welcome to this other edition of our Numerical Method 2 class. Yesterday we started with a tutorial series. And as you can see on the slide, I gave the indication for exercise 1.1. And then we did this one, exercise 1.2. We partially solved exercise 1.3, 3A. We did this one, 3A. Now for B, I gave you the hints on how to proceed. Right. At this level, you just use a change of variable. Integrate f of x and write it in terms of the integral of g t. And we know that if you integrate gt from 0 to 1, okay, so if you integrate gt from 0 to 1, then the right hand side will be this integral because it will be exact, right? For this polynomial, for this type of polynomial. But now, if g is neither of this, therefore it will be an approximation. Don't forget, if this g is an arbitrary function, like in this case, you will no longer put equal, but you put approximately equal to, right? Because we use this fact to determine the w's, right? Once you have the w and you want to derive the formula for an arbitrary function, which is no longer one of these, that is 1 and t, because this g is arbitrary, right? At this level. Therefore, when you write this integral in your change of variable, you say approximately equal, and then you substitute this. I hope you tried that because I asked you to do that yesterday. I hope you try it. Okay, so exercise 1.4 is similar to this one. The difference is that instead of trapezoidal rule, we are using Simpson's rule, right? A method of undetermined coefficient is exactly the same thing. We take gt equal to 1, then t, and finally t squared. And right, that is exact for this. We solve for the three coefficient or the three wave, W0, W1, W2. And similarly, we use the change of variable to integrate. Now, instead of the integral 0, 1, we have an integral 0, 2. Why? Because with the Simpson's rule, we have two subintervals from 0 to 1 and then from 1 to 2, two subintervals. And it will be virtually the same. And you should recover exactly the same root as the one given to you in the notes. Because when you write this, you should get exactly that same. All right. So in the directive or in the hint that I gave in the notes, I mean, not in the note, but the slide here. Okay, so this is 0, 1. So this is a step. You write this in terms of that. This alpha will be the coefficient that we will determine. It will appear automatically. This is 0, 1. So you write this integral from this, because you replace your x with this value. Once you replace with this value, your f becomes this, gt. You replace with gt. Now the dx is this one. You replace your dx by dt. So you see that this h already is here. You will take it out. So this alpha is likely your h or something. So when you will solve, you will see exactly what it is. or it will be h by 2 because of this w. So you have to play around that. No. It's when you replace the integral with this. Then your 2 will also appear from the coefficient, and therefore you recover the rule. So do that. 5. Determine the number n and the subinterval width h such that the composite trapezoidal rule for n subintervals can be used to compute the given interval with an accuracy of 5 into 10 to the negative 9. And then you have 3 integrals that are given. So you are going to apply this for to each of these integrals. Okay. What I want to draw your attention on is that if you look at the procedure in the notes and the procedure that we follow in the notes, it will depend on the integrand, that is the function that you are integrating. In this case, the integrand is this, our f of x. Here, let me, so this is our f of x. That's why you use in your rule. And here, f of x is 1 by 5 minus x. And obviously you have a and b. So for the first one here, a is negative 5 by 6 and b is 5 by 6. A here is 2, b is 3. Here a is 0, b is 2. So you have all that you need to start and to perform the job. And this is our tolerance. Okay, now what you will need here to determine the value of n here, remember, you need the error term. If you recall. And now, what is the error term for the trapezoidal rule? I want somebody to tell me. Because if you don't recall that formula, you're not be able to do this. I'm listening to you. What is the error term for the trapezoidal rule? What is this equal to? If you don't answer, I will skip this question and I will continue. You are not spectators. You are here to participate. You are here to learn. So I will wait. If you don't say anything, I skip that question and move to the next one.
Say
I'm listening.
Say it's negative b minus a um f to the power of 2. Okay, there's a 2 there, and then there's
There's a 2.
by on top of the f in brackets.
Ah, and you don't know what it means.
I do, sir.
What is it? If you don't know, it means that you cannot apply it. If you don't know what that 2 means, it means that you cannot apply it. How will you apply it if you don't know what it means? It's not a power. That's why you have in bracket to indicate that it's not a power. Otherwise, you could have just said f squared. It's not a power. I explained that many times. What is it? If somebody knows, he can contribute fast because you don't need to waste time. When you write like that, what does this mean? Because if you don't understand, it means you will never apply it. What is it? When you write it this way, what does that mean? Nobody to answer. Aaron free, say something. Okay, continue. So here we have this psi, which is unknown. Right? We don't know it. That's why we will compute an upper bound of the error term. Okay, the continuation. Yes, continue, Johannes. And what else? There's something else we need to add here. And then we divide.
Then there's 8 squared divided by 12.
Divided by what?
By 12, sir.
Good. Now you see that this h, if you express, okay, at this stage we can even leave. But if you express this h, n will appear, right? This n will appear. And how do you write your h? What is h? H is equal to what?
B minus A divided by N.
The number of subinterval. Good. Okay, so this is the formula. And in order to do this, so to find an upper bound, because we want to get rid of this, right? This is unknown, of course. It is in the interval AB. The open interval. So you don't know it. So because you don't know it, you need to take the maximum of, so this is the number of times you differentiate. Whatever we wrote in the Newton, if you recall the Taylor expansion, we wrote this. Right, if you recall. And this is our polynomial. P and H. This indicates the number of derivatives. Because if you don't put this, you want to differentiate, let's say even 7 times. What are you going to do? If you want to differentiate 7 times, are you going to do this? 1, 2, 3, 4, 5, 6, 7. Or if you want to differentiate 10 times, are you going to do this then that number of times? No, you just put this to indicate that you differentiate that number of times. So it's not a power of f or f to the power of that. No, it indicates the number of times you differentiate the function. I'm really surprised, huh? We have been using, since the first semester, we have been using that notation. And you people, when you write a test, instead of putting that in bracket, you just write f to the, it's completely wrong. If you differentiate a certain number of times, you have to put that in bracket, except you put a dash. If you do this, f if you do this, f prime is correct. If you do this, instead of 2 here, it's correct. You do that, 1, 2, 3, it's correct. Even if you do this 4, you can put a number of dash you wanted to indicate the number of derivative. It's still fine, it's correct. But if you come, you write this to say that you're differentiating 2 times, this is a power of f. This is not a derivative. So if you write the formula, Taylor expansion, and you do this k, this is wrong. And be warned, I will not be lenient if you make such mistake again. Because I've been warning you since the first semester, but people still do this. Because it's inadmissible that you graduate with a degree in mathematics when elementary stuff like this you don't know. And then you'll be doing honors. It's elementary question you cannot answer. Because you have been experiencing that. Okay, so I was saying, since this is unknown, you cannot use this formula because of the presence of that psi. So in order for us to use this formula, we need to find an upper bound on the error term. So we know that this error term will be less than or equal, because I take the absolute value. Then we get this b minus a, because b is greater than a, so the absolute value will be minus a, right? A square here, and we have by 12 here. Obviously, we have absolute value of this term, and then we take the maximum, right? This is what we have if we take absolute value. This will be less than or equal to that. Actually, it's still equal, right? Because if I take absolute value, this is equal, actually. When I say less than or equal, is, of course, if it's equal and you say less than or equal, it's still the same. It's still true. But actually, it's equal. This is equal to that, right? Still equal, just apply the absolute value. But now, since this is not known, to get rid of this, I take the supremum on x, on the variable here, on the interval AB, which I will call x. So this will be less than or equal to b minus a into a squared by 12. And then now I will write the max here, or the supremum, max sup. Of course, we can change that sup to max. For some reason, I will not indicate here. Okay, now I can take x here on the closed interval AB, like this. Now I'll take the second derivative on x, like this. So this is less than or equal to that. But now this one, I can find this. This one, I can know it. I need to find this. This is m. I call that m. I call this m for maximum. And you need to find that. And in order to find that, what are you doing? It's optimization. Full stop. This is the key. If you don't get m, you never get capital N, the number of subinterval. You never get it. Never. The key, when it comes to using the error term to find the number of subinterval or the step size such that there is a certain accuracy, as we did in class, you need to find that supremum, that maximum of the function that appears in your error term, which is the second derivative in this case. You need to find its maximum on the limit of integration. That is the interval AB. That is the key. And this one, you did it in calculus. Extreme of a function. You have the first derivative, how do you call it? First derivative rule or what? We have the first derivative method or rule or test. First derivative test. Yeah, that's the word. We have the first derivative test. We have the second derivative test. It's up to you. And depending on the function, the method will change. And when I say method, the way you approach it. Because when we are looking for the extreme or the maximum local, no, this is global on the interval AB. You need to know the critical point. That is the roots of the derivative of the function. Be careful here. In fact, this is really a waste of time, because I don't want to start explaining this to you because you did it already. If you don't remember, go and read your note. I'll be wasting my time to explain this. You did that in calculus. Because I see people, they don't even know how to find the extreme of a function anymore. Once you have passed a module, you forget about everything. If you forget, that's your problem, because I'm not in this class. There's no section where I will be teaching you how to find the extreme of a function. This one is a prerequisite. Please go back and read that. Otherwise, I will be wasting time. I will not cover what I'm supposed to cover. So I'm just insisting that you have to find the maximum of this. You have to find m. And for that, I refer you back to your calculus where you did optimization or finding the maximum, minimum of a function. You do it, you apply it to this. Go and read your notes and try to practice on that. And during the first semester, that was in numerical method 1. numerical method 1, I released a tutorial sheet where you were asked to find the maximum of functions. You can also go back to that tutorial sheet and try to do those problems to refresh. Okay, so now let us come back to this. This is our function. We have the cosine, we have this one, and we have that one. You see that the way I will approach each one will be different, because here, cosine function, if I take cosine function, the cosine function behaves like this, it oscillates, right? So it is not a monotonic function. So when the function is not monotonic, I need to find the turning points. I take the turning points, which are in fact the critical point, and the end points. I compute the value of the function at those points, and I take the maximum of those. Right. So these are things that you saw you tackle in calculus when we're computing the extremes of function. When you are computing, or when you are looking for the extreme in a closed interval, you also take into account, because this is not global, but it is in a particular sub-interval. So if there's no turning point there, it means that the function is monotonic. And if it's monotonic, it becomes easy, right? If a function is monotonic, it becomes easy to find the maximum. For instance, if the function is monotonic, it can be something like this, or it can be something like that. That's a monotonic function. Now, for this interval, assume that my interval AB is this one. If I want the maximum, it will be here, because the function is increasing, right? It will be the value of the function. So the maximum here will be f of b, because it's monotonic. Similarly here, this is monotonic, but it's decreasing. So the max for this one will be f of a for this case. But if the function is monotonic, I need to find the turning points. So that's why I'm saying it is not because in the tutorial you saw we took f of one of the point, that in each and every question you will see you just take f of the point. No, it means that you didn't understand what was done in calculus. It means that your calculus knowledge is zero, because if you can just for any question just take, because oh no sir, in class, because I remember a student told me, no sir, but in class the problem you took f of that point. I said, but are we dealing with the same function here? Are they behaving the same way? It means that the student doesn't even understand what he's doing. When you compute the extreme, it depends whether you have a monotonic or a non-monotonic function. That is extreme of function. Calculus, maybe you should be calculus 1 or 2 or whatsoever. Please go and revise that. Okay, I'm done with this, with that part. So that's what I wanted to stress on, so that when you solve, you should be very careful not to make those mistakes. Good. The next one. Okay, 6. We did 6 already, so you should be able to tackle 6. 7 is similar to what we did in class. So take your time to do that. Now, exercise 2. Exercise 2. Okay, so this is exercise 1. Now here we are in exercise 2. Okay, exercise 2. The first one, find the roots of the following Legendre polynomial. P2. In class, we did something similar. No. I asked you to do the 2-point rule. 2 points Gaussian rule. So it corresponds to this, because if you solve this, it will give you the roots. Method of determining coefficient, and then, of course, I'm talking about 1 and 2, all right? Question 1 and question 2 of exercise 2. Because question 1 and question 2 are related. If you look at question 1, you will see that you are asked to compute P2, P3, P4. And in question 2, you are asked to find the 2-point, 3-point, and the 4-point Gaussian quadrature formula. They are related. The two are related. Because to find the 2-point rule, I need to find Q. And that Q for our case is P2 here, because the rule of, remember that the Legendre polynomial, I explained that yesterday. The Legendre polynomial gives you Qn. Qn. If I have 2 points, then it will be Q2. And that Q2 in this tutorial sheet is what we are calling P2. P for polynomial, just for polynomial, right? But once you are told that these are the Legendre polynomial, you understand that P2 is exactly Q2. It's just a matter of notation, right? So P2 here is Q2 in the note. P3 is Q3. P4 is Q4. So if you get them, it's equivalent to the Q in your theorem, as I explained yesterday. You find the root, and that's the question you are asked to do here in question 1. You are asked to find the root, because you'll be using these roots to state the 2-point, the 3-point, and the 4-point, because you have P2, P3, and P4. So those two questions are related. The first question will be used in the second one. I'm guiding you, right, for you to understand why you need that first in the second. Once you get the roots, you can write the formula. The next thing will be to find what? The weights. And to find the weights, there are two methods. Either you integrate the what we call that is here is Legendre, the other one is what? Of course, we call that cardinal function, right? Cardinal function, the cardinal function L, those L. Remember that W. Remember that the Wi, the weight. For both Newton codes and the Gaussian, it is the integral from A to B, the limit of integration of L. Li, if you put K here, you put K also here. So these are the cardinal function, Li, dx. Obviously, if you recall how you write the Li, where Li Lix, if you recall how we did that, we say you take the product, because you have x minus x, of course, if you take your variable here to be j, from 0 to n, xj, and then here, now this one, because if in the numerator you have minus xj, in the denominator you must also have minus xj, so it will be the same. But the x here on top, below, because you take this, you put below, but your x become this. You see, this index I will be the same with this one. And because this should not be 0, you say j different from I. And this gives you a polynomial of degree n, right? Because if you multiply from j running from 0 to 1, You have a polynomial of degree n plus 1, but you remove 1. That is, a j will run from 0 to 1 except one value. So actually you have n factors. So it gives you a polynomial of degree n. Okay, so you see, that's how you remember. You see, I didn't read it anywhere. It's just a strategy to remember. Each time you write the cardinal function, if the strategy is already there, you just write it. You don't need to memorize anything. If you understand, you have understood, and you write it without any confusion. So this is what you'll be integrating. So now it's up to you to judge whether you are comfortable with this formula and you are comfortable with the integration of that without making any mistake. If the answer is yes, then for your WI, just use this. If it is no, go for the method of undetermined coefficient, because I think that one will be easier for you, because you write a system that you solve. Full stop. Than to try to find the LIs and all that. If you make a mistake, finish. The rest is 0. So make sure you study the method of undetermined coefficient well and you master it well. Okay. Yeah, so these are the 2 ingredients that you need to do question 2 for the 2.3.4 point Gaussian quadrature formula. Obviously, the 3 point we covered that already in class. We did it. 3 point, 2 point. I asked you to do that as a homework. It's even easier than the 2 point. Now, the novelty here, what is new here, is G4. That is the 4 point Gaussian quadrature formula. That's what is new, right? So the first step is to solve P for x equal to 0. So I will give you 5 minutes to solve that and tell me what you've obtained. So I will just do this. P4 x equal to 35x to the 4th minus 30x squared plus 3. Now, you see where numerical method is good. Now, you see, if you can write a good computer program that will approximate, because actually the computer program will approximate, except you use symbolic computation. We call it what? Computational linear algebra. Except you use such a software that will give you roots with radicals, right? With radicals, if there's a square root, you will see the square root, not approximation, it will give you the exact value. But that's only possible up to 4th degree polynomial, because from the 5th degree, it's no longer possible to obtain your root by radical, right? Okay, this is from a theory that you call Galois theory. Galois theory. It's in the Galois theory that you know that if you have a polynomial from degree 5 upward, you cannot solve it with radical the way you solve, we get the exact value using radicals. It's not possible. So the only way out is to use a computer program approximation. Of course, in general. Okay, so I'm giving you 5 minutes to solve this analytically, because you can solve this analytically and get all the 4 roots. And I also want you to explain to me the technique that you use to solve it. Obviously, there are 4 roots, eh? Polynomial of degree 4, there are 4 roots. And each root will appear with its negates, right? That is, if x is a root here, negative x is also a root. That's a remark that I made already last time. I said that for this Legendre polynomial, all the roots are real. That's the thing. But you also have roots with their negates. And if the degree of the polynomial is even, like in this case, 0 will not be a root. But if the degree is odd, 0 will be a root. Why? Because you need, because there is a symmetry about 0 when it comes to the root. So if you have the degrees of the polynomial is odd, symmetry around about 0, so 0 will be a root already. And then for any positive x, its negate will also be a root. So it gives you a total of an odd number of roots. But if it's even, because for any positive x, you have the negate, 0 cannot be there. So bear that in mind when you compute the root, to make sure that you are not getting something that is wrong. Those are just a few observations about these roots, the roots of this polynomial. I'm not talking about general, talking particularly for the Legendre polynomial. Okay, is there anybody who is finished? I want your contributions. Who is finished? If you computed the root, can you share with us? Or you are still busy computing the root? Can somebody share with us? Nanona, what have you done so far? Nanona? Can you quickly share with us before we part? What have you done? How did you proceed? Who can tell us the way to to go? If you let this, if you want to solve this p for x equal to 0, how do you proceed? Obviously, this is equivalent to 35 x to the 4th minus 30x squared plus 3 equal to 0. Now, from here, what do you do? How do you proceed from here? What is the next step from here?
Say, what about the 8?
If I put 8 here, isn't it the same if I remove the 8? If I multiply both sides of the equation by 8, isn't it the same?
Okay, say what I did.
Yeah, from here, what is the next step?
I implied a variable. I said let u be a squared.
Very good. So this is the key. So once you do that, the rest should follow. Okay, thank you so much. That's all for today. See you on Friday. Please take time to do the tutorial questions, prepare well, read the note, make sure you understand everything, and prepare well for Monday. I wish you all the best. God bless you and see you on Friday morning. Bye-bye.